Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 7, Organic Chemistry 2. Today we will continue on chapter 2, Aromatic Compounds. In the previous lecture we covered introduction to aromatic compounds, nomenclature of benzene derivatives. Today we will talk about structure of benzene, stability of benzene, and aromatics. Structure of benzene. In early 19th century, 1825, the English scientist Michael Faraday isolated a pure compound of boiling point 80 degrees Celsius from the oily mixture came from rendered whale fat that used to illuminate the streets of London and other cities. The molecule was named benzene and was eventually shown to have the molecular formula C6H6. Benzene has 4 degrees of unsaturation satisfied by a 1,3,5 cyclohexatriene structure, 1 ring and 3 double bonds that exchange their location, first proposed by Hückel and Schmidt. Yet it doesn't exhibit the kind of reactivity expected for a conjugated triene. The two drawings left here are now viewed as a resonance. So to have an equilibrium sign is wrong, but we can say they are two resonance structure, not an equilibrium. This is right. The aromatic moiety is particularly stable, much more than expected. So if we have ene, we add bromine, the brown color liquid disappears. And the product is addition reaction to give the dibromo compound. In benzene, no reaction. However, it reacts when we add Lewis acid like iron 3 chloride. Even though the monobromo product out of the first reaction, when we brominate further, we get 3 different isomeric dibromo isomeric product. 1,2, 1,3 dibromo, and 1,4 dibromo. If the 1,3,5 hexatriene structure is correct, then we should get 2 isomers of 1,2. 1 bromine between double bond, and the other one will be 2 bromine on a single bond. But that's not the case. It's just only 1,2 dibromo, 1 isomer. This is again support the structure of resonance structure, which is this one, and the carbon-carbon bond is not double bond, is not single bond, and we can see that in X-ray analysis. All carbon-carbon bond length 1.394 angstrom, and the bond length is 1.5, while if we have carbon-carbon single bond should be 1.48, and the double bond 1.34. So we have an average length 1.397 angstrom, which again in support of this structure. One more evidence came from the stability of aromatic moiety when comparing heat of hydrogenation for similar compounds. If we hydrogenate cyclohexene compound with only 1 double bond, we get a release of energy. It's exothermic reaction, 28.6 kilocalorie per mole. When we hydrogenate 1,4, we get double this amount exothermic, so it is minus 57.4 kilocalorie per mole. When we hydrogenate 1,3 conjugated double bond, we get minus 54.9 kilocalorie per joule. It's a less energy, which is more, means that 1,3 is more stable than 1,4. Yes, it's indeed, because we are expecting a resonance delocalization on the 1,3 cyclohexadiene. When we do that for the triene, we were expecting, our scientists were expecting minus 85.8, 3 times that amount, but we end up with only minus 48.9 kilocalorie per joule. This means that benzene is more stable than the proposed cyclohexatriene by about 36 kilocalorie per mole. We call that stabilization energy or resonance energy. As you can see, these compounds, all these compounds, when reduced, they gave the same compound, cyclohexane. Okay? So, the unusual stability of the aromatic compound benzene, okay? Now we will try to figure out why. How we can explain that, rationalize why benzene ring is more stable than expected. Source of stability. Bimolecular orbital of benzene showing overlap bonding takes place between orbitals, loops of equal faces. A phase change is indicated by a nodal plane dashed line. As the number of such planes increase, so does the energy of the orbital. So as you can here see, here is one node, here is one node, here is two nodes, here is three nodes, which means that as we increase the nodes number, we get increased energy. Scientists were able to calculate psi 1, psi 2, psi 3, psi 4, 5, and 6. They found out that in benzene, psi 2 and psi 3 are equal in energy, psi 4 and psi 5 are equal in energy. The group in the bottom, psi 1, psi 2, psi 3, we call them bonding molecular orbitals. Psi 4, psi 5, psi 6 are anti-bonding molecular orbitals. Now we have only 6 pi electrons. Okay, so we have to psi 1, we put 2 electrons, and psi 2, again 2 electrons, psi 3, 2 electrons. So all these electrons are in the bonding molecular orbit. We go to compare that to the hexatriene in open structure. We have 6 molecular orbital as we have before, and again 2 in here, 2 in here, 2 in here. We compare the total energy of the electron in the hexatriene with benzene ring. Cumulative energy or the sum of energy are lower in benzene, much lower. That's why benzene is more stable. So the source of stabilization of benzene is the lower energy of its molecular orbital. Hückel's rule. Scientists started studying the reactivity and stability of many cyclic polyene compounds to put their hand on why some compounds are aromatic, some are not aromatic or anti-aromatic. They study Cyclo Octatetraene C8H8 and cyclobutadiene C4H4. They are similar to benzene C6H6. However, they do not show aromatic stability. For example, the Cyclo Octatetraene adds bromine to its double bond to form the dibromo plus the enantiomer, of course. The cyclobutadiene is also unstable. It reacts with itself at minus 78 degrees Celsius via Diels-Alder reaction to form this species, which further ring opening to form the cyclooctatetraene compound. So both of them are not stable, even though they are cyclic and conjugated by system. These observations indicate that the presence of fully conjugated ring of pi electrons is not the sole requirement for aromaticity. The number of pi electrons in the ring is also important. When we have even pairs of electrons, this species is not aromatic. When we have odd, like 3 in benzene, then it's aromatic. Again, here in the cyclo octatetraene, 4 pairs of electrons is not aromatic. These two compounds did not show stability. So Hückel's rule stated that number of pi electrons, if it's equal to 4n plus 2, where n is a whole number, then the compound is aromatic. So if in case of benzene, 6 pi electrons equal 4n plus 2, and n will be equal 1, so benzene is aromatic. Another way to explain the stability or instability of the cyclopolyenes is by electron distribution of their electrons on molecular orbitals. But how can we draw the molecular orbital of cyclopolyenes? Back in 1953, Frost published an article describing this method for drawing out the energy level of cyclic systems, with simplified version as follows. He said, we draw a circle, and inside the circle put the polygon or the structure of the cyclic system inside the circle where the vertex point down. So triagonal, we have the vertex down, so we have 2 up here. So we said here 1, 2, 3. For the cyclopute, the vertex down, you have 2 in here, 1 up, 4 molecular orbitals. Well, if you have cyclobent, the vertex down, so we have 2 in here and 2 up beside the lowest state here. So 5. For the benzene, vertex down, 1, 2, 3, 4, 5, and 6, and go and so on. He said in the middle of the circle have a line. What's above the line is anti-bonding. What is below the line is bonding. What about the one on the line? Non-bonding. So for the cycloprop, we have bonding 1, we have 2 anti-bonding. For the cyclobute, you have 1 bonding, 2 non-bonding, 1 anti-bonding, right? Let's go and apply that. Do the molecular energy diagram for cyclobutadiene and Cyclo Octatetraene appear to be particularly stable or unstable configuration, and explain. We have here 4 electrons by electrons, psi 1, psi 2, psi 3, psi 4. As we mentioned, here is bonding, give it 2 electrons. Now anti-bonding, non-bonding. For non-bonding, we give 1 because they are equal in energy. We give 1, we give 2, and they are going to be better in spin. Right? Cyclobutadiene, highest lying electrons in non-bonding orbital, psi 2 and psi 3, and are therefore reactive. According to Hückel's rule, the compound exists as a diradical 2 Amer electrons in its ground state. Such a diradical is expected to be extremely reactive. What about the Cyclo Octatetraene? Again, we have 8 molecular orbital. We have 1, 2, 3 bonding, psi 1, psi 2, psi 3, and we give each one of them 2 electrons, so we are done with 6. We have 8 electrons, so left 2. We give it to the non-bonding. Again, it's very similar to cyclobutadiene. So we have 1 here, 1 here. So this compound is reactive again. It's not aromatic. To summarize the criteria for aromaticity, the compound must contain a ring comprised of continuously overlapping p orbitals, should be planar molecule. The number of pi electrons in the ring must be Hückel's number. So compounds that fail the first criteria are called non-aromatic. Compounds that satisfy the first criteria but have 4n electrons rather than 4n plus 2 are anti-aromatic. Hexa-1,3,5-triene is non-aromatic. It's not aromatic, it's not cyclic. Cyclobenta-1,3-diene is not aromatic, non-aromatic. This carbon is sp3 hybridized. There is no b orbital. What about Cyclo Octa-1,3,5,7 tetraene? Again, this molecule is not planar. they found that this molecule is like top, so it's not planar. 6-annuline cyclic system with conjugated 6 electrons. Benzene, yes, it's aromatic. Annuline 10, non-aromatic. Why is that? The hydrogen atom positioned inside the ring, shown in red here, experiences steric hindrance that forces the compound out of planarity. Since the molecule cannot adopt a planar conformation, the p orbitals cannot continuously overlap with each other to form one system, and as a result 10-annuline and 14-annuline do not meet the first criteria of aromaticity. In the 14-annuline does not bear the hallmark aromaticity, aromatic properties, which about the chemical stability. It quickly decomposes when exposed to light and air, even though in the proton NMR it showed the hydrogen, these hydrogens at 7.8, which downfield in the aromatic area, even though. So you will find that talk about the 14-annuline. In some books they put it aromatic, in another non-aromatic. But at least you know why. It is not planar 100, okay? But the criteria of aromaticity using proton NMR about the deshielding of these hydrogens, if you have a continuous wave of pi electrons, create a field that take these hydrogens downfield, and they are in the region of 7.8, and again the protons inside here highly shielded at minus 0.6. So it's a debate between people saying it's aromatic, people saying it's not aromatic. Predict whether the following 18-annuline will be aromatic, non-aromatic, or anti-aromatic. Explain your reasoning. This molecule contains 18 electrons, so applying Hückel's rule 4 plus 2, where n equal 4, so this molecule should be planar. There is no, as you can see in the 3-dimension, there is no steric effect. It's planar, n equal 4. It is aromatic compound. Classify the following compounds as aromatic, anti-aromatic, or non-aromatic. For the bicyclo 441 Undica 13579 bentaene, replacing the hydrogen in 10-aniline with bonds to bridge carbon allows all C bond to be approximate on the same plane. Thus obey Hückel's rule, aromatic, n equal 2. Its aromaticity is confirmed by two main pieces of evidence. First one, the similarity of carbon-carbon bond length as measured by X-ray. We said if it's decolized, so it's not single bond, carbon-carbon single bond, neither carbon double bond carbon. So it's in between, okay, and that's what they found by X-ray. Second one, proton NMR display influence of the diamagnetic ring current, which is characteristic for aromatic compounds. So these hydrogens will appear in the range from 7 to 8, which is the case, okay? For the compound trans-dimethyl dihydropyrene. This compound has in the middle, okay, 2 trans methyl group. So this is 14 aniline with interior 2 sp3 carbon, allows all carbon-carbon pi bonds to be in the same plane, thus obey Hückel's rule, and it's aromatic with N equal 3. Its aromaticity is confirmed by 2 main pieces again: the similarity in carbon-carbon bond length from X-ray data. Second, the proton NMR display the influence of diamagnetic ring current, which is characteristic of aromatic compounds. The 2-methyl group showed at upfield minus 4.25 parts per million. Okay, the outside goes up to 7 and 8. Okay, and the inside the ring goes upfield. Okay, so it showed up at minus 4.25, which is very clear for the diamagnetic ring current. And that's published in Journal American Chemical Society in 1995. Pyrene. Pyrene is aromatic despite its violate Hückel's rule. It has 16 pi electrons instead of 14 to obey Hückel's rule. But one of the pi bond is not participating in delocalization, so it cannot be considered for 4n plus 2 electrons. It has only 14 delocalized pi electrons, and it's aromatic. Pyrene is cyclic, pyrene is planar, pyrene has 14 delocalized pi electrons, the pi electrons outside here. Okay, that's 14 pi electron. Every atom in the ring structure of pyrene is sp2 hybridized. One of the following compound is much more stable than the other two. Classify each as aromatic, anti-aromatic, and non-aromatic. Of course, if it's aromatic, that means it's stable. Benzene, 8 electrons, that's 4n rule, it's anti-aromatic. Azulene, it's 10 pi electrons, and it's 4 plus 2 rule, Hückel's rule, it is aromatic. This is the one which is stable. Now we look for the heptalene, 12 pi electrons, so it's 4n rule, it is anti-aromatic, highly unstable. Polynuclear aromatic hydrocarbons. They are composed of 2 or more fused benzene rings, like naphthalene, C10H8. Fused ring, 2 benzene ring together, fused. The 2 aromatic rings in naphthalene contain a total of 10 pi electrons. It has less than twice resonance energy of benzene. So the total for naphthalene is 60 kilocalorie per mole, 30 kilocalorie per mole per ring, where in benzene it's 33 kilocalorie per mole. Drawing it in Hückel structure, we can find here is benzenoid-like ring. But here we have benzenoid-kininoid structure. This is not the benzene Hückel structure, this one. So we call it kininoid. Again, here is benzene, okay, but here is quininoid. That's why it is less in the stabilization energy than benzene. Anthracene, C14H10, has a resonance energy 84 kilocalorie per mole, or we can say it's 28 kilocalorie per mole per ring. Remember once again, benzene has 36 kilocalorie per mole stabilization energy. Well, Thus, it is more reactive than benzene. Anthracene undergoes 1,4 addition at 9 and 10 position to give a product with two isolated, fully aromatic benzene rings. When we draw again Hückel structure, we can find here benzenoid ring, quininoid ring, benzenoid, quininoid, benzenoid, quininoid, benzenoid. As you can see here, only one like benzenoid structure. Here is one, here is two, like the one in naphthalene. Here is two. So according to drawing resonance structure, yes, we can expect that it is less stable than benzene, but still we draw it on this structure in the text, and you can see clearly when you draw it with the nowadays program, they showed you a complete resonance delocalization of electrons in naphthalene ring, fused 3 rings. When we add bromine to anthracene, color disappear, and we get 9,10 dibromo 9,10 dihydroanthracene in cis and trans mixture. Remember that you are here, according to this simple mechanism here, you are creating carbocation which is delocalized, okay, all around the conjugated system. Okay, so you have here several other resonance structure. That is the most stable, where you have a complete benzenoid ring. Then that's you end up with 9,10 dibromo. Okay, so it's not like the alkene when you have the trans, when you get the bromonium ion. Okay, you get here carbocation delocalized intermediate, benzenoid. You can get also Diels-Alder for this species. It's here diene-like, dienophile in maleic anhydride. You get the Diels-Alder adduct in very good yield. Phenylphrene, again, it is isomer from anthracene. It has C14H10, but it has higher resonance energy. It is 91 kilocalorie per mole. Divide that by 3, so it's 30 kilocalorie per mole per aromatic ring. The compound again has 14 pi electrons in its 3 aromatic rings, compared to 18 electrons for the 3 separated benzene ring. When we draw the resonance structure, Hückel's structures, we can see clearly that we have 1, 2, 3, 4, 5 resonance structure. Remember, in anthracene we have only 4. So we have extra structure, resonance structure, which means that it is more stable. Yes, it is here 30 kilocalorie per mole instead of 28 kilocalorie per mole. We can find that in this resonance structure, we have one of the 5 benzenoid, right? So it is more stable. Again, we draw it this way, and the 3D of nowadays programs show that complete delocalization of the pi electrons. over the 3 rings. So it is more reactive than benzene? Yes. That's why when you add again bromine, you end up with a 9,10 dibromo 9,10 dihydronaphthalene in cis and trans mixture. But when you heat this compound, you end up with 9-bromo phenylphrene. You end up with 9-bromo phenylphrene via E1 mechanism, which means that upon heating it goes back to here and then Br minus instead, because you're giving energy driving force for this to act to get this. Oops, you get that, right? See you next lecture.